ओके जी। हमने वैसे लास्ट लेक्चर में भी डिस्कस किया था एवीएल ट्री, लेकिन आप लोग नहीं थे, मैंने लेक्चर अपलोड नहीं किया, तो मैं दोबारा स्टार्ट से ही एवीएल ट्री डिस्कस करता हूँ। ठीक है जी। तो एवीएल ट्री स्टैंड्स फॉर एडेल्सन, विल्स्की एंड लैंडिस ट्री। बेसिकली दीज आर थ्री साइंटिस्ट हु एक्चुअली इन्वेंटेड दिस ट्री। ठीक है जी। तो लेट्स डिस्कस कि ये होता क्या, व्हाट दिस एवीएल ट्री इज। सो रिमेंबर दिस इज अ बीएसटी। कोई कंफ्यूजन इसमें तो नहीं है? This is a BST because you have one on the root, then you have a bigger value on its right side, then you have another bigger value on further right, and so on. So all the bigger values are on the right side of a root node, and there is no left child of any child. So all these values are actually null values. So that was a this first one was a BST, but the shape of this tree, it's called the skewed shape. Okay, it's a skewed shape and it's skewed towards the right. Okay, so it's skewed towards the right, whereas this second tree, this is actually a very symmetrical tree. We can see that the shape is exactly like a triangle. So this is a symmetrical tree, but having said that, is this a BST or not? That's the question. Because we saw that the BST is a better is a tree that can actually capture the entire essence of searching. Remember, so BST is a better tree. So uh, if you just check the root node, it has all the smaller values on the left side, bigger values on the right side. And similarly for two, smaller values are on the left side and the bigger values on the right side. So this is a BST as well. If you look at the right subtree as well, so this is a BST, and the shape is just like a triangle. So this is a symmetric shape. Now, if I try to search something in this tree, I would start from the root node. Remember, and if the value to be searched is bigger than this value on the root, then I would go on the right side. So I would take exactly the branch that I need to go. Okay, a bigger value would be on the right side. For example, the value that I'm searching is 5, then I'll go towards left of 6. So I'll find this 5 by just taking 2 steps, and I will reach this node 5. So a search tree actually gives me the capability to know that where the value would be found in this tree. So instead of going on all the branches and following a BST or DFS, BSF or bet for search or depth for search, BFS or DFS, I exactly know which branch do I need to take to reach a specific value. If the value is there, then it would be found. Otherwise, I can return false, that the value is not found. So having a smaller branch is desired. Whereas we saw in the previous example, if a tree is skewed, it still is a BST, but the search takes more number of steps. So in this first tree, if I try to search 7, it would take exactly 6 steps. Or if I want to compare the values, then it would be 7 steps. I would compare this the value with 1, then 2, 3, 4, so on. At the seventh comparison, I would find the value that 7 is in the tree, and it's the child, it's the leaf node. So a search in a skewed tree is actually not very efficient. Instead, if I have a symmetric tree, then the search is very efficient. So a BST alone is not an efficient tree. A BS tree with a symmetric shape, just like this triangle, is actually desired, and that's the efficient way of storing the data uh, to search a value from that data. Okay, so this is what we are going to achieve. We are trying to achieve here. Okay, how can we reach this symmetric shape? That is, if I talk about the properties that I discussed in the previous lecture, I discussed about a few properties. The first property was that a tree can be a complete tree. Remember? Then I said that a complete tree is not possible all the time. So we actually relaxed the condition, and we said we can have an almost complete tree. Remember? So we can have an almost complete tree. That's one way, but that tree should be of a shape that all the levels above the last level should be complete, and on the last level I can fill the values from left to right. Okay, that's the condition of a complete tree, remember. But a complete tree, the problem here is that for a complete tree, if I want to maintain the BST property as well, then this is very difficult. Okay, because on every insert I would have to reshuffle the values, and I would have to maintain this BST property as well. So having a BST all the times is not possible for an almost complete tree. Okay, so and the second thing that we discussed was a full tree. Remember? So for a full tree, what we saw that a full tree is a tree where all the nodes have either two or one child. Okay, so this condition actually does not give me the option or the symmetric shape. A full tree could be like this node has two children, then this other node also has two children, another node has two children. So a full tree can also be a asymmetric or skewed tree. So both these definitions are not of any significance here. So in order to keep this symmetric shape, I need something like this, the tree on the right side or something on the tree on the bottom left. But still, the definition that I would actually try to achieve here is the definition of a balanced tree. Okay. So now we'll see, okay, how we can achieve this balance in a tree. But if I have a balanced tree, definitely what I essentially have is that whenever a branch gets longer than the other branch, I would need to add some nodes on the other side as well. So this, if I try to keep this balance after every insert or delete operation, then definitely what I would achieve is a symmetric tree, right? And Hashish, what you are saying is the correct complexity that if I search in a symmetric tree, then the search would take like if I start from the root node and I reach to a leaf node, that would be order of log of n. Um, you can actually reduce this from the data, but this n is equal to the number of nodes. So here I have 7 nodes, so a search operation would take log base 2 of 7 number of steps. That would be around 2 steps, right? 2 point something. Definitely that's 2 point something, but that's the maximum number of steps that a search operation would take in this balance tree. So let's see how we can make this balance tree. There would be some definitions, and then we'll actually reach the final conclusion that how can we maintain this balance in a BST. So the essence here is that if I have this tree, which is of course a BST, if I insert a value 2 in this tree, what I would have is that I would add this 2, I would compare with 6, I would go towards left, then I would compare with 4, I would go further left, and from 1, I would go on this side and I would add 2 here. That's the insert in a BST, remember? So inserting 2 in this balanced tree would make this branch a little lengthier than the other ones. So adding to or adding anything into a base tree definitely affects the properties of maybe the balance property and the BST property as well. So I would have to reshuffle the tree and achieve this metric shape somehow that all the branches, this was a lengthier branch, this branch again gets equal to other branches. And the branch that was smaller, that maybe this branch, it still has some nodes. So I would pick some nodes from this side and move them towards the other side of the root node. In this way, what I would achieve is that this longer branch, it would actually be shifted upward, and a node would slip towards the right side. Hence, actually, I would achieve the balance on both the sides. So that's the overall concept that an AVL tree actually has. Okay, so what we take from this slide or this overall discussion is that we definitely need to run some procedure on a BST if I insert or delete something from that tree, because an insert or a delete operation definitely affects the balance of a tree, right? Okay, so moving on. So what exactly is an AVL tree? AVL tree is a good, but it's not a perfectly balanced tree, because if we try to keep a perfect balance, which means that all the nodes they have equal height. A perfect balanced tree is that all the branches are of equal length. But at some time, I might have some nodes, some additional nodes that if even if I move this one node from this side to another to the other side, I would have the tree like this. So I do not have these branches of equal length than the other ones, right? So if I compare all the branches are not of the equal length, which means that I cannot maintain this perfect balance. It's not necessary that all the branches are of equal length. So what we actually allow is that we actually allow not a perfect balance, but we allow a balance factor to be maintained. So the balance factor is that the height for every node, heights of left and right subtree can differ by no more than one. So which means that the tree on the left, if I did draw it, I have, for example, I have this node, then I have, for example, this is a tree. On the root, the height of the left subtree is this subtree. The height of this subtree is one, and the height of right subtree is zero. So the difference is one. So that's the property of balanced tree. For the perfect balanced tree, I would have the equal heights of both the trees, but for a normal balanced tree, I can have a difference of one in both the subtrees. So this tree actually fulfills the property of a balanced tree, but not the perfect balanced tree. Okay, so in avial tree, that's a good tree, means it's a balanced tree, but it's not a perfectly balanced tree. So that's a little slight relaxation that I would give this avial tree. So having this relaxation actually gives me an edge that I would have lesser adjustments in the tree than I would have to make if I try to make a perfectly balanced tree. Okay, everything's clear. If you have any question, you may ask. Hashir, Hatim. Okay, Hashir. Please go ahead if you have a question. Or should I move on to the next slide and keep discussing until you come up with the question? Okay, Hashi, the question is why is it that we can't aim for absolutely balanced tree? Is it a harder problem than almost balanced? Definitely. Remember, in this slide, I discussed that if we add a value in a balanced tree or in a symmetric tree, I would have to make some readjustments just to maintain the symmetric shape. And if I try to keep this complete or perfect balance, then definitely these adjustments would be a lot in number. Having not a perfectly balanced or just having a balanced tree, where we allow a difference of one between the heights of left and right subtree, would actually reduce the number of adjustments. And what we want to achieve is that our search operation is faster. It should not take more than log of n number of steps. So that the requirement actually a normal balance tree, it also fulfills that requirement. A perfect balance tree definitely would be better in search, but still that would be around one step not more than one step. Okay, because what we are allowing here is that we can only have a branch lengthier than the other one, with only a difference of one node. So the path that is lengthier would not be more than one in length. Okay, so the difference would be not more than one. So that's not what we can say is that we are not achieving much by having a perfectly balanced tree. It's exactly, if we take the order of the performance, then the order is exactly log of n for both perfectly balanced or a balanced tree. The difference is of only one step. So that one step we already know that we ignored that one step. Okay, so we are not aiming for the perfectly balanced tree because we achieve the same performance for both of them, right? Okay, so okay, let's move on and see how an AVL tree, how we can actually judge if a tree is an AVL or not. So now we have to match actually two conditions. The first condition is that the tree should be a BST, and second condition is that it should be a balanced tree, not a perfectly balanced. Okay, so we would allow a difference of one. The balance factor should be 0 or 1, okay, or -1 as well. So for this tree on the left, uh, if I have 5 on the root node, then I have all the smaller values in the left subtree and the bigger values in the right subtree. Similarly, for 2, I have smaller value in the left subtree and the bigger values in the right subtree. Then for the 4, I have a smaller value in the left subtree. For 8, I have a smaller value in the left subtree. So this is a BST. Good. Okay. For balance, I would check the balance of root node. So for root node, the left subtree that is rooted at 2, it has the height of this longer branch which is equal to 2. So the height of this node is 2, or this subtree is 2, and the height of this right subtree is actually 1. Remember, the height is, if I check the height of the tree rooted at node 8, I would go to the lengthiest branch and I would count the number of steps. So there is only one step here from 8 to 7. So the height of this tree is 1, and height of the tree rooted at 2 is 2. So the difference between the height of left and right subtree for 5 is 2 minus 1. So this is the balance factor of this node, which is equal to 1, and this is good for a balanced tree. Similarly, I'll check this balance or balance factor on all the nodes. So if I check this balance on node number 2, I have the height of left subtree as 0 and the height of right subtree as 1. So the balance factor is, again, for this 2, the balance factor is equal to 0 minus 1, which is equal to -1. Okay, so the balance factor, the allowed range is, or the possible values are between 0, -1, 0, and 1. I can only have any of these three values. Okay, so -1 is also good for this, for the balanced tree. So 2 is also balanced. For 4, the left subtree has height 0 and the right subtree has height. What's the height of a null node? Remember, we discussed it. -1. Okay, so this is -1. So the difference for the balance factor for node number 5 is, balance factor for node number 5 is 0 minus -1, which is equal to +1. So this 4 is also balanced. Similarly, 8 is also balanced. So all the nodes, they have the balance factor intact, or in the range of 0 to -1. So this tree on the left is an AVL tree. Whereas the tree on the right, clearly we can see that this branch is a lengthier one. Let's see if it's lengthier than the difference between left and the height of left and right subtree is more than 1 or not. So for this node 7, the left subtree has height, the tree on rooted at 2 is 1 and 2. The height is 2. Okay, the height of this node is 2 and the height of this node is 0. So the difference balance factor for this root node 7 is equal to 2 minus 0, which is equal to 0. So this violates the balance property of the AVL tree. Okay, so I haven't checked BST property, but because I knew that there is some violation in the balance, I just found that the root node is not balanced. So that's enough to prove that the tree is not an AVL tree. Otherwise, if the balance of all the nodes is actually in the limits of -1 and 1, then I would also check the BST property. Okay, so an AVL tree maintains two properties. The first property is that the tree should be a BST, binary search tree. And adding on to that definition, a BST that is balanced is called an AVL tree. So the simple definition: a BST that is an AVL that is balanced is an AVL tree. Okay, so I check the balance at root node, which is not in the limits of -1 to 1. So this node 7 is not balanced, which means this tree is not an AVL tree. If there is an imbalance on any single node, the entire tree is not an AVL tree. Okay, so now I hope everyone can identify an AVL tree and actually pick up can try to pick up the difference if the tree is not an AVL tree. Okay, so we have to check two properties. The first property is that the tree should be a BST, and the second property is that the BST should be balanced. Okay, so let's move on to the next slide and see. So the overall summary is that we would have a balance factor that should be between -1 to 1. Okay, and the height of null node is -1. That's the summary of the entire discussion that we had. So just the variation of height, we already had this, so I would just skip it. You can see that the height of this node is 1, height of this leaf node is 0, height of this null node is -1. So we already know that we already calculated all these heights and balance factors. So let's just skip this slide and move on to the next slide and see. um, uh, what we discussed in maybe two slides before that, if we insert or delete something into an AVL tree, it may disturb the maybe the BST property or the balance property. So we would try to come up with a procedure that both the properties are maintained. So if I just try to insert something into an AVL tree and I want to maintain the BST property, Kashif, can you tell me what should I do if I just want to maintain the BST property? How can I insert a node into an AVL tree?
सर चेक करते जाएंगे नोड बाय नोड वेयर वी हैव टू पुट द वैल्यू
What you essentially mean is that we can just perform the BST insert operation. Remember? So that operation is that we
यस
actually
सर
check the magnitude of the new node and we compare it with the root node, and then we would decide if this value would go on the left side or the right side. And every time a node is inserted, it is inserted as a leaf node. Okay. Okay, so if we follow the BST insert operation, then the BST property would be intact. Okay, now the second thing is how can we make sure that the balance property remains intact even after a new insert or a delete? We know that these two properties can be disturbed, but we can manage the insert by using the BST insert. But for balance, we need to do something new. Okay, so this is the challenging part here in the AVL tree. How do we insert or delete something from an AVL tree, keeping the balance property intact? So we'll see in the coming slides how we can maintain that balance property. So um, for example, these are two different trees, and we insert the same value 7 in both the trees. So for the left subtree, that was an AVL tree. Of course, this branch was smaller than the other side, than the left side. But if I insert 7 in this branch, now this branch is, the length of this branch is equal to the length of the longer branches. So this does not violate any balance property. So an insert in an AVL tree may not disturb the balance property. If we if we just add as a BST insert, the tree would still remain an AVL tree. But the tree on the right side, if I insert 7 in this tree, I would go towards the right of 6, then I would go towards the left of 9, left of 8. So this 7 on the left of 8 If I now check the balance of the nodes above this 7, uh, before adding 7, the balance factor of 8 was 0. Left and right both were minus 1. So minus 1 minus minus 1 was 0. But now I have a left child. So the balance factor of this node 8 is now not 0. It's now it's plus 1. And the height is also changed. Okay, so what there actually the difference there are actually two changes in this tree now. The balance factor of a few nodes is changed, and the height is also changed. Okay, so let's see. This 8 still is balanced because the balance factor is 1, but for this node 9, the height of left subtree is now 1, but the right subtree has height minus 1. So 1 minus minus 1 is equal to 2. So that's what's written here. This 9 is not balanced anymore. Okay, so we would have to adjust this node now. How we can do that? That's a simple trick, but the first step before the adjustment is to identify which node is actually not balanced now, or which node has violated the property of balance. Okay, so in this slide, we have just identified that that this node 9 has violated the balance factor property. Okay, so we would adjust this node. Okay, um, anybody, can you guess if I adjust this 9, and for example, if I adjust this 9, what the tree I would have is something like this. For example, if I just do something like this, now this is a balanced tree. I have just made an adjustment that I have pushed this 9 downwards and pushed this 8, or pulled this 8 upward on the place of 9. So I came up with this tree. Now this tree is balanced, right? But I want a comment from you guys. If I just perform one adjustment in an imbalanced tree, do I need to check further for an imbalanced node or not? Or should I stop the adjustment process? Like in this specific tree, I just made one adjustment and the subtree became balanced. And then should I check this root node as well? Maybe there is a case that if I adjust this part of the tree, still there is some imbalance on the upper part of the tree. Can there be a case? Kashif, you said no. Is this the answer? Okay, you say no need to check. Any reason why we should not check any node above this adjustment?
सर बिफोर द इंसर्टिंग हमारे पास पहले ही बैलेंस था, तो अगर हमने इंसर्ट किया तो अनबैलेंस हो गया वो एक सब ट्री। जब उसको बैलेंस कर दिया तो पीछे तो पहले से ही बैलेंस थे सारा ट्री, तो देयर इज नो नीड टू चेक।
ठीक हो गया। तो आप जो कह रहे हैं कि if I just make an adjustment and I balance this part of the tree, if you just look at the adjustment that I've made is that before the adjustment, this branch was lengthier, remember? And the issue was after the addition of this node 7. If I just made the adjustment to pull this 7 one step up and pull this 9 downwards to increase the length of the shorter branch, the height of the remaining the resultant tree would be the same as the tree before inserting 7. And if the height of this tree remained the same as it was before inserting 7, then this 6 would see no difference in its balance factor when it would compare the height of left and the right subtree, because this h is again the same before inserting 7. So if this h was previously, maybe this is hr for h right, and this is hl for h left. So if hl minus hr, it was actually less than equal to For example, if I take absolute values less than equal to 1, then if this HR is again, I made the adjustment, and I actually somehow uh, made sure that this does not change, then this relationship stays intact. ठीक है जी, बात समझ आ गई ना कि अगर मैं जो प्रीवियस हाइट थी दैट वाज एच आर, अगर मैं कोई एडजस्टमेंट करूं और इस राइट साइड की हाइट स्टिल इट रिमेन्स एच आर, इट मीन्स दैट द डिफरेंस बिटवीन एच एन एंड एच आर रिमेन द सेम. If the difference remains same, then this 6 would see no difference uh, that it needs to make any adjustment. Okay, so if I make only one adjustment, if I just adjust one imbalanced node, then the entire tree would be AVL tree again. Okay, so that's an insight that you should actually understand. Let's see a few more scenarios and finalize the discussion here. Okay, so the overall process is, if I make an insertion or deletion into an AVL tree, what I would need to do is to perform a transformation on the tree, or we can say, if I just use the correct word, that would be I would perform a rotation in the tree to make it AVL again. So in order the transformation or the rotation, it would follow these two rules. The first rule is the in-order traversal of the transform tree is the same as for the original tree. Remember, the in-order traversal for a BS tree is, if I make an in-order traversal in a BS tree, what I would get is I would get a sorted data. Remember, in a base tree, if I first read, for example, the left node, then root, and then right, it would be 1, 2, and 3. So that's sorted data. So after the transformation, the resultant tree should be a BS tree. This first property says that. And the second property says that the height balanced property should be maintained. So that's the rules that this transformation would follow. Okay, the transformation is that I just showed in the previous slide, that I would make some adjustment, some transformation. The correct word is I would perform a rotation on the tree to maintain these two properties again. Okay, so that's how we actually keep a tree AVL even after insert and delete operation. Okay. So uh, what we would do is that if we just made an insert or a delete operation, let's just talk about insert first. Okay, if we just make an insert in an AVL tree, what we would do is that we would check the balance vector of the nodes, and for we would check only the balance vector of the nodes on the path on which this new node is added. Okay, like for in this example, when I added 7 here, I just check this parent 8, then the grandparent 9. So I would only need to check the path on which this node is added. I do not need to check all other paths for imbalance, because a new node is added here, and the height or the balance vector is only disturbed on this path. Okay, so if there is an imbalance in the tree, it would be on this path. Okay, so that's the first thing that we should note, that we would check the balance vector of all the nodes from the new node, the leaf node, till the root node on the same path where the node is added. Okay, we will not check in the rest of the tree. Okay, the second thing is that if we find an imbalanced node, then we would call that node number A. Okay, we would name it. Okay, we would call that node A. So the balance vector of node A is disturbed. If we find that node, then we would perform an operation that is called a rotation on that node A. Okay, so what we would essentially do is that we would actually do something like this, that we call the operation rotation on the node A. So that would be something that we would do when we would find a imbalanced node. Okay, so let's see how we can do that. This is an example of a single rotation on an AVL tree. This is the same tree that we just saw in the previous slide, and I showed you the readjustment that was the tree on the right side. But what essentially we did was that we actually kept this 9 node here. What you can say is that we had a row. Now I'm actually marking these red, and you can say that this red line, this is a row. Okay. Okay, so I have a row. I hold this row from this corner and I pull it towards this side. And I have a pulley on this place. That's the node A. Okay, so I would place a pulley on this node A. Remember the pulley experiment that you did in physics, maybe in your secondary education? Remember? So if I pull this row from here, what I would do is that uh, I would pull this 9 over here, and this 8 and 7, this branch would actually go upwards, and 8 would take the place of 9. So all the nodes on this branch, I would pull them upwards, and from this position, I would pull them downwards. So what I would have is that if I pull these nodes upward, I would pull this 9 downwards. 8 would take the place of 9. 9 would go downward, and 7 would go upward. So this would be the final shape. And if I just tell how or why we call it a rotation, is that this is the direction in which I have actually rotated the nodes. The entire tree is this subtree is rotated towards right after this operation. So this operation is called a single rotation, or you can say single right rotation. Single rotation towards right. Okay, so that's the adjustment that we would make in the tree on the node A to make it height balanced again. So formally, what a right rotation is that if I have a case where the node A, it has the imbalance towards its left of left. So the imbalance is that the imbalance is towards the left of node A, and this node B is child of node A. Then the imbalance is towards further left of node B. Okay, this C could be an entire subtree, but the difference is that the tree on the right of B is smaller than the tree on the uh, left of B. Okay, so the height imbalance is towards the heavier side is towards the left of B. Okay, so this node A is imbalanced, B is not imbalanced. The difference between this red part and this red part is 1, but the difference between if I just change the color of the pen. So this this branch towards left of A, and this branch green branch on the right of A, the balance factor here is 2. Okay, means the height of this height of B and whatever node here at maybe we can say X. So the difference between H of HB and HX, that is 2. Okay, A is imbalanced, but the heavy side is towards left and further left of its child. Okay, so that's the case when we would have to perform a single right rotation. Okay, so the procedure is that what I told you, the easier way to remember is that we would place a pulley over here, and I would pull the rope towards right from A. A would go downwards, B would go upward, and C would also go upwards, and the resultant tree would be like this. But a hidden step is that what I showed that this B could have a right child as well. This is a simple example. You cannot see here, but we would see in the coming slides. In fact, we would actually run a um, um, complete example. We'd have that we would insert in at least 15 to 16 values, and we would maintain the AVL property. So we would see all these rotations there, and you would see the scenarios when this node A is imbalanced, but this child, this left child, has both the children. In that case, this second step is there, or you can say um, this second step. Okay, so the second step is that when I would pull this A towards right, this connection here, the child of B, the child of B, it would actually rotate its connection from here to this side. That's the hidden step here. So this child of B, this right child of B, it actually detaches itself from B and move its connection towards this position. So after this rotation, the node that would reach here would become the parent of this green child. So that is node number A. So if I just draw this green child here, it was somewhere around here. But after rotation, as I said, it would detach itself from this side, from the left side, and it would move towards the right side. So it would become the child of this node. Okay, so that's the final step in the rotation. Otherwise, the rotation was very simple. I just pulled the pulley and went downwards, B and C moved upward. But the hidden thing is that this B also, it may also have some children. So if it has some children or a subtree here, that subtree would detach itself from the left side and it would go to the right side. And if I just see this value here, it is bigger than B. Remember, कुछ वैल्यूज डाल देते हैं. फॉर एग्जांपल अगर ये शेप है, ए की वैल्यू में भी हम कह सकते हैं जी कि 5 है, बी की वैल्यू फॉर एग्जांपल 3 है और सी की वैल्यू फॉर एग्जांपल 2 है. तो ये सी शेप होगी. अगर यहाँ पे कोई वैल्यू आ सकती है तो दैट वुड बी 4. ठीक है जी. तो अगर यहाँ पे 4, इसके नीचे भी कोई ट्री था जिसकी वजह से इम्बैलेंस बना था ए पे, लेकिन इफ आई हैव दिस 4 हियर, तो when I rotate this tree, this 4 became, this A was 5, the left child of 5, and B was 3. So this 4 is now towards the right, or this 4 is now in the right subtree of 3. So this adjusting this child is also important, because this actually maintains the first property, that the BST, the AVL tree is also a BST. So moving this 4 from this side, from the left side towards the right side is important, because this 4 is bigger than B, the value 3. Okay, so that's an important step here. So don't forget this step, this second step, that A takes the ownership of B's right child. This is the B's right child. Okay, so that's single right rotation. If you have any confusion, you can ask. Okay, so if there's no confusion, I can move forward. So after single right rotation, I would have a single left rotation as well. So in that case, I would place the pulley here and I would pull this A towards left side. So that's a left rotation. This direction is towards left. Okay, so that's a single left rotation. And similarly, in the single left rotation, this B could have a left child. And if it has a left child, then this left child would detach itself from this side and it would attach itself towards the left side. Okay, so definitely B is a bigger value. For example, this is 6, so that value, the child of B is towards just left, so that's a smaller value. We can say it's 5. So if I move 6 on the root, then this 5 should be in the left subtree of 6. Okay, so that 5 would be attached here. Okay, so that's the second step. That's important. Don't miss that step. Okay, we'll see in the example that I would actually show you in maybe after a few slides. So that's single left rotation. So we have discussed two rotations: single right rotation, single left rotation. Okay, so sometimes this single rotation, it does not fulfills the, or it does not gives us the exact output that we want. For example, in this tree, I have this side heavy, this right side is heavy for this A. And from the child of A, that is C, I have the new node added on this branch. So this is actually the case where the new node is inserted towards the left of right child. Okay, the new node is inserted towards the left of right child. C is the right child, so the new node is added towards the left of right child. So this case is actually a zigzag case. Remember, the previous case was that the node was added towards left, right of right, or left of left. But a separate case is when the value is added towards left of right, or on the other way. Similarly, I can say that the if I take this example, the value is added in the right child of left, left child. Okay, so the value is added in the right subtree of left child. So these are two different cases. Values added in the left subtree of right child, or the values added in the right subtree of left child. Okay, this is the left child. This point is the left child, and the value is added towards the right of the left child. And in this case, this is the right child, and the value is added towards the left of the right child. So these two cases are a little different or difficult to handle. So essentially, if I just perform a single rotation and the value is added towards the right side, I can say that if I just rotate this tree towards left, then I can get a balanced tree. So let's rotate it. So the rotation would be that for this node, I have A here, C here, and B here. If I just pull it from, I place the pulley over here below this node A, and I pull it here. What I would have is that A would come on this place, right? C would become the root. Where would this B go? This B would actually detach itself from this side and would attach it towards this side. So B would come here. Remember the single rotation, single left rotation that we just discussed? This child, this left child of the right child, it actually detaches itself from this node, from the right child, and moves its connection towards the left side. So B is connected to this node A. So I get to this shape. After performing a single left rotation on this tree, I get this tree in the center. Okay, I say if I try to adjust this tree using one single right rotation, once again what I have is that this I would pull this C downwards. I would place the pulley here. So C would go downwards. C would reach here. A would become the root node, right? But this B would detach itself from node A from the left side and move its connection towards the right side. So B would be connected here. So I came back to the same previous state. Got it? So whenever I have a zigzag shape like this one, these two shapes, a single rotation does not happen. Performing a single right rotation on this tree would actually transform this subtree into this subtree, this shape. And performing a single left rotation on this subtree would transform this subtree, this shape uh, into this shape. Okay, so whenever I have a zigzag case, I cannot solve this using a single rotation. Okay, formally, what I would need to do is a double rotation, and the double rotation is like first, if this node A is the imbalanced node, I would not adjust this one. I would actually adjust its child. What I would do is that this B is inserted, like this B was inserted in the inside of the tree. If I see, previously I had for a single rotation to work, I had a shape like this one. That was the skewed shape, right? Remember, I discussed this shape as skewed. So I had this skewed shape. Or the other name that I can give it is that I had, if this is the root node, either I had the insertion like this or insertion like this. So I had these two cases seem like the outside cases on the outside of the tree. I have not inserted anything in the inside of the tree. Okay, so the outside case can be resolved by just rotating the tree towards the other side. If this left side is heavy, I would rotate towards the right side. If the right side is heavy, I can rotate it towards the left side. So the outside case can be resolved by single rotation, but this case, when this is, for example, the root node, I have inserted something in the inner side of the tree on these places. These are the inside of the tree. So I have inserted in the inside part of the tree, then a single rotation does not work. What I would have to do is that I would pull this inside node towards outside. So what I would do is I would perform a right rotation on node number C. When I would perform a right rotation, this B would go upward and C would go downward. I would get to this shape. This shape. See, the C was this B was here. I pulled it upward and it became the parent of node number C. C came downwards. So now this is an outside case and I can resolve this by just simply rotating it towards the left. So I rotated it towards the left and I came up with this shape. Got it? So if I have, overall, the cases are divided into four categories. Either it's a left outside case or a right outside case. If these are the two cases, I can simply perform the rotation on the other side. Okay, that the issue would be solved. The balance factor would be maintained. But if I have an inside case, then the first step would be that I would convert that inside case into an outside case, like this one. This tree on the left side was an inside case. So this tree, this was the case, the inside case. The value is inserted in the left subtree of right child. So this is an inside case. I transform this case into this one by just performing a right rotation on the right child. And now I have an outside case. I can just fix it by rotating this node A towards the left. So the first rotation is on the right child and the second rotation is on the root node or on the node that is imbalanced. Okay, so that's a double rotation. Okay, and the first rotation in this case is the right rotation and the second rotation is the left rotation. So this is the rotation on the child and this is the rotation on the parent. So this is also called an LR rotation. L rotation, yani left rotation is on the imbalanced node and the R rotation is on its right child. So that's an LR case. Similarly, vice versa, we can have an RL case as well. When the inside case is the value is inserted in the right side, right subtree of the left child. So in that case, I would have to perform a left rotation on the child, on the left child. That would make transform the tree into this left outside case. Then I can perform the right transformation on the parent. So the parent has a right rotation and the left child has a left rotation. So this case is called RL. Parent has the right rotation and the left child has the left rotation. So that's another double rotation. That's the exact mirror image of the previous LR rotation. ठीक है जी, कोई confusion तो नहीं आता? Because these are the four rotations that are the crux of this AVL tree. If you just understand these four rotations, then there is in fact, all the details or the complexities of AVL trees are now discussed. Okay, Kashif, you can ask the question if you have raised the question. Raise your hand.
सर आपने डबल राइट रोटेशन लिखा हुआ है तो व्हाट डज इट मीन?
डबल राइट मैंने आपकी आसानी के लिए लिखा है, ठीक है। मैंने एक्चुअली इसका डबल राइट जो नाम लिखा है ये शायद इसका मे बी आप टेक्स्ट बुक्स में ना देखें इसका नाम, इसका टेक्स्ट बुक्स में नाम होगा RL रोटेशन। ठीक है, लेकिन मैंने इसको डबल राइट ऐसे कहा है कि ऑन द पेरेंट नोड आई वुड हैव टू परफॉर्म अ राइट रोटेशन इवेंचुअली, लेकिन दिस रोटेशन इज नॉट अ सिंगल रोटेशन दैट आई नीड डबल रोटेशन। तो पेरेंट पे जो भी रोटेशन है उसकी अपोजिट साइड की रोटेशन उसके चाइल्ड पे होगी। तो दिस डबल राइट रोटेशन इज सिंपली कि मैंने टर्म को थोड़ा शॉर्ट कर दिए, दिस इज अ डबल रोटेशन, और जो पेरेंट पे रोटेशन परफॉर्म हो रही है दैट इज अ राइट रोटेशन। तो अगर पेरेंट पे राइट रोटेशन हो रही है तो चाइल्ड पे लेफ्ट रोटेशन होगी उसके अपोजिट डायरेक्शन में। तो आप ऐसे भी याद रख सकते हैं।
ओके
ठीक
सर,
है,
थैंक यू।
कि आप पेरेंट की रोटेशन को याद कर लें कि इट्स अ राइट रोटेशन क्योंकि उसके लेफ्ट साइड पे हैवी है, लेकिन उसका जो लेफ्ट चाइल्ड जो है वो आगे राइट साइड पे हैवी है। ठीक है, तो एक चीज और ध्यान रखनी है आपने कि हम जिस इम्बैलेंस नोड को पिक करते हैं उसके सिर्फ चाइल्ड को देखते हैं कि उसके चाइल्ड के आगे कौन सी साइड हैवी है। हम उसके आगे उसके पूरी हाइट को मैच कर रहे थे, लेकिन यहाँ पे सिर्फ एक स्टेप का डिफरेंस है। ठीक है, तो हमने सिर्फ चाइल्ड की लेफ्ट और राइट साइड को देखना है कि उनमें से कौन सी हैवी है। तो चाइल्ड की अगर राइट साइड हैवी है तो हमारे पास आर एल वाला केस है, अगर चाइल्ड की लेफ्ट साइड हैवी है तो हमारे पास एल आर वाला केस है। ठीक है जी, तो ये चार हमारी रोटेशंस हो गई थी। तो ओवरऑल ये वही दैट्स अ स्लाइड दैट वी डिस्कस्ड अर्लियर के द प्रोसेस इज whenever we add a new node, we check all the nodes on the path on which this node is added. If we find an imbalanced node, we call that node number A, and then we perform a suitable rotation on that node A. And there are four cases of these rotations. First, we'll check the case if it's an outside case or an inside case. If it's an outside case, we would perform the appropriate single rotation. And if it's an inside case, then we would perform the appropriate double rotation. Okay. So overall, if it's an outside case and the insertion is into the left subtree of the left child, remember this is just the left child. Okay. We'll see, we would traverse only up till the left child and see which side is heavy. Okay, we will not go down further. Okay, so if we have a left of left is heavy, then a single right rotation is required. And if right of right is heavy, then we will just perform a single left rotation. Okay, so left rotation. And for the inside cases, we will perform two rotations. And if the right subtree of left child is heavy, that is the right subtree of left child. And the last point is left subtree of the right child. Okay, so for this case, we would perform an RL rotation, and for this specific case, we will perform the LR rotation. So these are two double rotations. So let's see how we can do that. That's the pseudocode of overall rotations. We would add this code into insert as well as the delete operation. Okay, both the functions, both the operations would have some structure like this structure that is shown here. If the tree is right heavy, if the tree is right subtree is heavy, is left heavy, that's the double rotation. Right subtree is left heavy, that's the double rotation. Otherwise, that's a single rotation. And if the tree is left heavy, then if the left subtree is right heavy, then the double rotation. Otherwise, that's a single rotation. That is left of left is heavy. Okay, so let's add these value. You can write these values on your copies, and we would add this value into an AVL tree one after the other. Okay, so there's a question. I'm consulting a text on them, and it mentions that the height has a lower bound determined by Fibonacci. Are we going to look at that stuff too, or is out of scope? It's out of scope, but you can see that maybe you can see if it holds or not. We would not discuss that here. Okay, we'll do RB tree as well since those are compared to trivial. No, we would not do red black trees. We actually used to discuss red black trees, but then we saw that as it's just an alternate to an AVL tree, and maybe it's not very essential to know that there are some trees that are of somewhat similar complexity of AVL tree. Instead, we discuss some other trees like B trees, B plus trees, heaps that are definitely that have some different structure than an AVL tree, and they have some other applications. Red black trees and AVL trees, they can be used alternately on the same problem. So if we just know the AVL tree, we don't need to discuss the RB trees. Okay, but we used to discuss them. If you want to take those lectures, I have those slides ready. I can share them with you, so you can see some examples of a red black tree, or we can discuss them later. Maybe if you can come to the campus and we can discuss them as well. Okay, but in the course we have removed RB trees from the syllabus. इनफैक्ट आरबीटी जो है ये शायद किसी और यूनिवर्सिटी में डिस्कस भी नहीं होते। हम लोग डिस्कस करते रहे हैं, लेकिन मे बी एक या दो टर्म्स हुई हैं हमने आरबीटी को डिस्कस करना छोड़ दिए। Okay, so let's insert these node and try to maintain the AVL tree, and we would actually do all the rotations as well. So we have an empty tree. Let's add this 3 in that tree. So if I add 3 in that tree, that would become the root node, right? Okay, after inserting 3, the next value is 2. So if I perform a BST insert, that 2 would go towards the left of 3. So 2 would become the left child of 3. अभी तक मेरे पास सिर्फ 2 नोड्स हैं, तो डेफिनेटली एक पेरेंट होगा, दूसरा चाइल्ड होगा, तो बैलेंस तो डिस्टर्ब होने का कोई सवाल ही पैदा नहीं होता। लेकिन अगर मैं चेक करूं, तो जो नया नोड ऐड किया, मुझे इसके पेरेंट का बैलेंस चेक करना है अप टिल द रूट नोड। तो ये जो 3 है, इस 3 का बैलेंस फैक्टर मेंटेन है। इसके लेफ्ट सब ट्री की हाइट 0 है, राइट सब ट्री की हाइट -1 है, तो बैलेंस्ड है। अच्छा, नेक्स्ट वैल्यू आ गई जी 1। तो 3 से छोटी है, 2 से भी छोटी है, तो जाके 2 का लेफ्ट चाइल्ड ऐड हो गया। ठीक है जी। अभी अगर आप देखिए, जब 3 नोड्स आए, तो अब मैंने 1 नया नोड ऐड किया था, इसके पेरेंट का बैलेंस चेक किया, तो लेफ्ट सब ट्री की हाइट 0, राइट सब ट्री की हाइट -1, तो 0 माइनस -1, तो इसका बैलेंस फैक्टर है -1। ठीक है, या +1, विच इज फाइन। लेकिन जब मैं फर्दर रूट पे गया, तो 3 के लेफ्ट सब ट्री की हाइट है 1 और राइट सब ट्री की हाइट है -1, तो 1 माइनस -1 इज इक्वल टू 2। सो दिस 3 इज इम्बैलेंस्ड नाउ। तो मुझे इसके ऊपर क्या परफॉर्म करना है? दिस इज द केस के लेफ्ट पे ऐड है, दैट्स एन आउटसाइड केस। ठीक है जी, आपने फॉलो करना है। मैं वो सारे केसेस 1 बाय 1 डाटा के साथ आपको दिखा रहा हूं। तो जब मैं लेफ्ट का लेफ्ट केस है, तो आई वुड परफॉर्म अ सिंगल राइट रोटेशन, दैट्स एन आउटसाइड केस, तो सिंगल रोटेशन इज रिक्वायर्ड, और एडिट ऑन द लेफ्ट ऑफ लेफ्ट, सो दैट्स अ राइट रोटेशन। ठीक है जी। तो रोटेशन इज कि आई वुड प्लेस द पुली हेयर बिलो दिस नोड नंबर 3, and I would pull the rope from the right side of 3. So when I would pull 3 downwards, it would reach here, and 2 would go upwards and become the parent of 3. 1 would still remain the left child of 2. Had I had the right child of 2, then that right child would have become the left child of 3, लेकिन यहाँ पे है नहीं है। ठीक है जी। तो ये that's the final shape of first single rotation towards right. Okay. So after inserting 1, I have to perform a rotation. Okay जी। So एक और चीज जो आप यहाँ से पिक कर सकते हैं कि whenever I have 3 nodes in an AVL tree, the only shape that it can have is this one. कोई भी और शेप होगी, that would be an imbalanced tree. Okay, क्या पॉसिबल शेप्स हो सकती हैं? या तो ये वाली शेप, या फिर ये वाली शेप, अदरवाइज ये शेप, या ये शेप। तो ये सारी चारों शेप्स जो है, ये इम्बैलेंस शेप्स हैं। सिर्फ जो एक पॉसिबल बैलेंस शेप है, दैट इज दिस वन। ठीक है जी। अच्छा, नाउ आई वुड हैव ऐड 4। तो एडिंग 4 इनटू दिस ट्री इज के 4 इज बिगर देन 2, 4 इज बिगर देन 3, 4 इज एडेड हियर। ठीक हो गया। पेरेंट का बैलेंस फैक्टर चेक किया, नजर आ रहा है कि लेफ्ट की हाइट -1, राइट की हाइट -1 -1। ठीक है, इस 4 की हाइट -1 -0, इस लेफ्ट साइड ट्री की हाइट 0 है, तो दैट इज -1, तो -1 इज फाइन। 2 को चेक किया, तो 2 के भी लेफ्ट और राइट साइड ट्री की हाइट में 1 का डिफरेंस है। नजर आ रहा है कि दिस ब्रांच इज 1 स्टेप लॉन्गर देन दिस वन। ठीक है, लेकिन आपको चेक करना पड़ेगा कि 2 के लेफ्ट सब ट्री की हाइट है 0 और राइट सब ट्री की हाइट है 1, तो द डिफरेंस इज -1। ठीक है जी। तो दिस ट्री इज बैलेंस्ड। ओके, अब मैं ऐड करता हूँ जी इसमें 5। लेट मी जस्ट erase these calculations from here। ओके जी, तो let's add this 5 in this tree, so that 5 would go towards right of 4. Now if I check um, the height of this balance, this node, this parent, 4, -1 -0, that is -1, fine. लेकिन जब when I check this balance factor of 3, that is -1 minus the height of this node, this subtree rooted at 4 is 1. So the balance factor is -2, which is out of the limits. So this 3 is imbalanced. So the case is this 3 is imbalanced. Let's call this node as node number A. Remember हमने ऐसे ही कहा था ना कि we call the imbalanced node as node number A. So the balance is right of right child. So that's an outside case. We would perform a single left rotation. ठीक है जी, तो I would place the pulley below this node 3 and I would pull the rope towards left. This 3 would go downwards here. This 4 and 5 would go upward. 4 would become the parent of 3 and 5. So the final shape would be 2 and 1 are already there, but I have made the adjustment in this subtree. So 4 has become the root of this subtree, 3 has gone towards the left, and 5 is still on the right of 4. ठीक है जी, तो दिस इज अ सिंगल रोटेशन। और अगर आप देखें तो इस 5 के ऐड होने से पहले ये 3 वाले सब ट्री की अपनी हाइट थी 1। अभी भी रोटेशन के बाद अब 4 उस जगह पे आ गया, इसकी इस सब ट्री की हाइट अभी भी 1 ही है। तो फॉर दिस टू देयर इज नो डिफरेंस इन द बैलेंस फैक्टर बिकॉज द लेफ्ट सब ट्री एंड द राइट सब ट्री दे हैव द सेम हाइट as they had before this adding this node number 5. Okay, so 5 is done. Now let's add 6. So anybody, I want somebody to help me here. um, अच्छा, आकिब आप बता सकते हैं 6 कहाँ जाएगा? आकिब आपकी आवाज नहीं आई
सिक्स सर
मुझे।
राइट साइड पे आएगा इधर।
बिल्कुल ठीक है। ठीक है, तो हम जब मैच करेंगे तो 2 से मैच किया, 4 से मैच किया, 5 से मैच किया, सबसे बड़ा है, तो 6 इधर और नीचे चला जाएगा। अच्छा, रिमेंबर वन मोर थिंग, बैलेंस फैक्टर डिस्टर्ब होने का केस उस तरह का होगा जब हम एक ही ब्रांच पे कंसेक्टिव 2 एडिशंस करेंगे, 2 इंसर्ट करेंगे, तभी वो ब्रांच 2 स्टेप बड़ी होगी ना। ठीक है, तो पॉसिबली किसी एक ही ब्रांच पे 2 इंसर्ट्स हो जाएं जबकि दूसरी साइड की ब्रांच पे उतने इंसर्ट ना हो गए। तो जब पहला इंसर्ट होगा तो वो ब्रांच अगर पहले इक्वल लेंथ की थी तो वो पॉसिबली एक लेंथ ज्यादा, उसकी लेंथ 1 स्टेप ज्यादा हो जाएगी, और जब दूसरा इंसर्ट होगा तो उसकी लेंथ 2 स्टेप्स ज्यादा हो जाएगी। दैट वुड बी द कंडीशन ऑफ इम्बैलेंस। तो यहाँ पे हम यही कर रहे हैं कि एक ही साइड पे सीक्वेंस में देखें। एक और चीज नोट करें, यहाँ पे भी मैं सॉर्टेड सीक्वेंस में वैल्यूज, तो एग्जांपल बनी हुई ही ऐसी है कि वैल्यू सॉर्टेड है जो एक ही सीक्वेंस में ऐड होती जाती है, तो ये एक ही ब्रांच में बार बार ऐड हो रही है, जिसकी वजह से हर 2-3 स्टेप्स के बाद मुझे एक रोटेशन करनी पड़ती है। ठीक है, तो ये इंपॉर्टेंट पॉइंट था यहाँ पे। अच्छा जी, तो मैंने जब यहाँ पे 6 ऐड किया तो 5 का बैलेंस फैक्टर भी डिस्टर्ब नहीं हुआ। आई हैव दिस -1 -0, तो बैलेंस फैक्टर इज -1, फाइन। 4 को चेक करें तो 4 के लेफ्ट पे हाइट है 0 और राइट पे हाइट है 1, तो 0 -1 इज अगेन -1, ये भी फाइन। अच्छा, अब हम चेक करते हैं 2 को, तो 2 के लेफ्ट की हाइट है, लेफ्ट सब ट्री की हाइट है 0, राइट सब ट्री की हाइट, इस 4 वाले ट्री की हाइट है 2। ठीक है, दिस ब्रांच 2, तो 0 -2 इज, तो ये द बैलेंस फैक्टर दिस 2 इज डिस्टर्ब। ठीक है, तो इसको अगर हम ठीक करेंगे तो हमने कहाँ पे एडिशन किया, अगर आप हैवी को चेक करें, अब यहाँ पे वो चीज इंपॉर्टेंट है नोट करनी कि मैंने जब इंसर्शन की है तो मैंने जब इम्बैलेंस नोड फाइंड किया, ये नोड 2 जो है इसको मैं नोड ए कहता हूँ, तो जो हैवी साइड है वो इसके राइट साइड है। ठीक हो गया, हमने राइट साइड पे पहुंच गए। अब राइट चाइल्ड पे दोबारा चेक करने की कौन सी साइड हैवी है, तो दोबारा राइट साइड हैवी है, तो द केस इज अगेन एन आउटसाइड केस, राइट के राइट पे हैवी है। ठीक है, जो इम्बैलेंस नोड है उसकी राइट साइड हैवी है, और जब राइट चाइल्ड पे पहुंच गई तो राइट चाइल्ड पे जाके भी हमने चेक किया कि उसकी राइट साइड हैवी है। बस ये दो स्टेप चेक करने हैं, इससे आगे चेक नहीं करना कहाँ गया वैल्यू। ऐसा हो सकता था कि फॉर एग्जाम्पल यहाँ पे 6 ऐड ना हुआ था, 5 के लेफ्ट पे कुछ ऐड हुआ था, स्टिल दैट वुड बी अ केस ऑफ आउटसाइड केस, कि जो इम्बैलेंस नोड है उसके राइट के राइट पे कुछ हैवी है। ठीक है, तो 5 के यहाँ पे भी एडिशन हुई होती ना, तब भी हम ये वाला सिंगल रोटेशन वाला केस ही पिक करते। ठीक है जी, ये बात समझ आती है सबको? तो तो वी वुड परफॉर्म अ सिंगल रोटेशन ऑन दिस नोट। ठीक है जी, तो अब अगर देखें तो अब ये वाला केस है जो मैंने आपको बताया था, वो स्टेप जहां पे इस राइट चाइल्ड का एक लेफ्ट चाइल्ड भी एग्जिस्ट करता है, इम्बैलेंस नोड के राइट चाइल्ड यानी कि नोड नंबर 4 का लेफ्ट चाइल्ड भी एग्जिस्ट करता है, तो अब ये चाइल्ड भी अपना कनेक्शन यहाँ से डिटैच करके इस साइड पे लेकर जाएगा। ठीक है, तो पहली रोटेशन तो ये है कि मैं यहाँ से इसको पुल करूंगा नीचे की तरफ, तो 1 और 2 दोनों नीचे चले जाएंगे, 4 5 6 तीनों ऊपर चले जाएंगे, तो 4 रूट पे पहुंच जाएगा। ये बात समझ आ रही है सबको? यहाँ से सारे नोड्स एक एक स्टेप ऊपर चले जाएंगे यहाँ तक, तो 6 ऊपर चलेगा 5 की जगह, 5 4 की जगह, 4 2 की जगह पे, और ये 1 और 2 नीचे चले जाएंगे एक स्टेप। जो 3 है ये सिर्फ अपना कनेक्शन जो यहाँ पे 4 के साथ कनेक्टेड था, ये अपना कनेक्शन लेफ्ट साइड पे मूव करेगा, जो भी नोड इस पोजीशन पे आएगा उसके साथ कनेक्ट होगा। तो अगर आप देखें तो 4 को हम रूट पे ले गए, 5 उसका राइट चाइल्ड, 6 उसका फर्दर राइट चाइल्ड, और 2 और 1 यहाँ से नीचे मूव हुए थे, ऐसे ही था। बीच में यहाँ पे एक अदर नोड पड़ा हुआ था जिसका नाम था नोड नंबर 3, और ये नोड नंबर 3 पहले इस साइड पे कनेक्टेड था, पहले इस साइड पे कनेक्टेड था, अभी अपना कनेक्शन यहाँ से ब्रेक करके दूसरी साइड पे कनेक्टेड। ये वो स्टेप था जो कि बीच में एक हिडन स्टेप था जिसको मैं बार बार रिपीट कर रहा था, ये आपने भूलना नहीं है। ठीक है, तो 4 का जो लेफ्ट चाइल्ड था वो 2 का राइट चाइल्ड बन गया। ठीक हो गया? तो अगर आप कनेक्शंस देखें तो कौन कौन से चेंज हुए हैं ओवरऑल, अगर मैं कहूं कि मैंने लेफ्ट और राइट चाइल्ड का पॉइंटर रखा हुआ था, तो 2 का राइट चाइल्ड अब चेंज हो गया। पहले 2 का राइट चाइल्ड था 5, पहले 2 का राइट चाइल्ड था 4, अभी 2 का राइट चाइल्ड है 3। तो एक कनेक्शन हो गया, 2 का राइट चाइल्ड चेंज हुआ। दूसरे 4 का लेफ्ट चाइल्ड चेंज हुआ, 4 का लेफ्ट चाइल्ड था 3, लेकिन जब ट्रांसफॉर्मेशन हुई तो 4 का लेफ्ट चाइल्ड हो गया 2। तो ये दो जो कनेक्शन थे, 4 का लेफ्ट चाइल्ड और 2 का राइट चाइल्ड, ये दो कनेक्शन नए बने, ये चेंज हुए। पहले 2 के राइट पे कोई और था और 4 के लेफ्ट पे कोई और था, अभी हमने उन दोनों को सिर्फ चेंज किया। गॉट इट जी? कोई कंफ्यूजन यहां तक? अच्छा, और अब जब स्ट्रीम में मैं 7 ऐड करूंगा तो 7 यहाँ पे के राइट पे ऐड हो जाएगा, जब 7 इधर ऐड होगा तो व्हाट आई वुड डू इज कि आई वुड जस्ट परफॉर्म, आई वुड जस्ट चेक के विच नोड इज इम्बैलेंस। 6 इज नॉट इम्बैलेंस्ड, 5 के लेफ्ट पे हाइट है -1, राइट पे हाइट है 1, तो -1 -1, so the height difference is -2, so this 5 is imbalanced। कौन सा केस है काशिफ?
सर राइट रोटेशन, सर आउटसाइड केस है तो लेफ्ट रोटेशन होगी एक्चुअली एंटी क्लॉकवाइज।
ठीक है, तो सिंगल लेफ्ट रोटेशन। ठीक है, तो सिंगल लेफ्ट रोटेशन जब परफॉर्म करेंगे तो 5 को नीचे पुल करेंगे, 6 रूट बन जाएगा, 7 भी ऊपर आ जाएगा। तो द फाइनल ट्री वुड बी 4 इज ऑन द रूट, 6 is its left child, 5 is 6's left child, 7 is towards right of 6, and 2 3 and 1। ठीक है जी, दैट्स द फाइनल ट्री। तो ये तो मैंने स्लाइड पे बनाया, लेकिन यू कैन सी द एनिमेशन हियर। ठीक है जी, आई हैव द कंप्लीट एनिमेशन ओवर हियर, ऑल द रोटेशंस आर परफॉर्म, so that's the final tree। Okay ji, we'll stop here for now, and we'll discuss a few more additions for double rotation cases in the next lecture। ठीक है जी, if you have any questions you can ask।